Hi, I'm John Barron from Google Research, and today I'll be talking about loss functions. Here's a common problem in machine learning and computer vision where we're trying to minimize some loss to recover some model parameters. Depending on your task, it can be really hard to determine exactly what loss you should minimize to get the best results. Today I'll be presenting a general family of loss functions with varying degrees of robustness, and I'll show that this family is a superset of a bunch of existing loss functions in the literature. I'll also be presenting an adaptive loss function that automatically determines which member of that general family to use, which allows training or optimization to determine its own robustness. Here's some toy data that I'll be playing with. Let's assume you want to regress from x to y. A reasonable way to do this is to minimize squared error, or L2 loss. And if your data is well behaved, this works out great. But let's add a few outliers to the data. And now we see that minimizing L2 loss doesn't work the way we'd like because our model is being dragged around by those outliers. So maybe you should change your loss function. Here's a popular choice, a pseudo-Huber loss. And this works better, but it's still influenced by those outliers a little bit. So you might go and read some papers and find some other robust loss functions. There's a bunch out there. Here's Welsh loss, which doesn't work too well for this data. Here's Geeman-McClure loss, which works pretty well. And here's Cauchy loss, which works slightly better. So we've got a model that we're happy with, but we had to manually try a bunch of different discrete loss functions to get here. It turns out, though, that all of those losses are members of a general family of robust losses, shown here. This family has a shape parameter that we'll call alpha. When alpha is 2, you get L2 loss. When alpha is 1, you get pseudo-Huber loss. When it's 0, you get Cauchy loss. When it's -2, you get Geeman-McClure loss. And when it's -infinity, you get Welsh loss. This loss has some other nice properties. It's monotonic with respect to its inputs, which is useful for annealing parameters. It's smooth with respect to its inputs. And you can bound its derivatives, which is useful for preconditioning and for preventing exploding gradients. To get a sense of how this family of losses behaves, it's helpful to look at the derivative of the loss. When alpha is 2, the derivative is linear, which means that larger errors result in larger gradients. When alpha is 1, the gradient saturates, which means that large errors have as much effect as moderate errors. Then, when alpha gets smaller, the gradient begins to redescend towards 0 as errors get larger. This means that large errors have less influence than moderate errors. Then as alpha continues to drop, the effect of outliers on the gradient becomes even smaller. So with this generalized loss function, it's straightforward to generalize an algorithm. You just take the loss function you've been using and add this alpha hyperparameter. And we have some results in the paper where we do this and show some modest improvements. But this isn't a super satisfying result, as now you've got this extra hyperparameter that you need to manually tune. Ideally, you'd like to just let alpha be a free parameter and solve for it during training along with the rest of your model parameters. But this doesn't work, because training will just cheat and change the shape of the loss function to trivially minimize everything. So to fix this, you need to instead minimize the negative log likelihood of the probability distribution that corresponds to the general loss. Doing this is a little tricky, but you can make it work by approximating the partition function with a spline. You can see why this works by comparing the general loss with this new adaptive version. The adaptive loss can't cheat, because if it wants to give a discount to outliers, it needs to pay an extra penalty on inliers, and vice versa. So this means you can just set alpha to be a free parameter, and training will just do the right thing, all without having to do any hyperparameter tuning. So here are some results where we take an existing model and swap in this adaptive loss. VAEs are a popular tool for image synthesis, and they usually work by placing normal distribution on individual pixels. And this exactly corresponds to minimizing our loss, but with alpha fixed to 2. But instead of a fixed loss on the pixels of an image, we can place an adaptive loss on a wavelet decomposition of the image and get nicer synthesized images and higher test set likelihoods. Our next task is self-supervised monocular depth estimation, where you're trying to train a model that predicts depth from a single image. Here's a recent paper on this task that minimizes a loss that is roughly within this family of loss functions. And here's what happens if you swap in an adaptive loss, again on a wavelet decomposition. You get nicer looking depths and a 17% reduction in error on the test set. So that's it. We've got TensorFlow and PyTorch code available online. Thanks for your attention.